Hello everybody, welcome to the Integral Calculus Quick Start Guide. In this guide we're going to talk about what an indefinite integral is. And by definition, the first thing you should know is that an indefinite integral is an antiderivative. Well, what's an antiderivative, you say? Well, it's exactly what it sounds like. An antiderivative is the answer to the question of, if we already know the derivative, what was the function that we took the derivative of in the first place? So for example, what function did I take the derivative of to get x squared in the first place? So you might think to yourself, there are some functions that would give me x squared. For example, I remember that when I take the derivative with respect to x of x to the third, I get 3x squared. Well, that's kind of close. The trouble is that we've got that 3 sitting around in front. Now, how would we undo that? Well, if I had 1/3 of 3x squared, sure enough, I would end up with x squared. So the derivative would have to be of the function 1/3 times x cubed, so that I would be assured of getting the derivative 1/3 of 3x squared, giving me 1x to the second. All right, let's think about something similar here. What derivative do I take to get x cubed? Well, once again, I remember that when I take the derivative of x to the fourth, I end up with 4x to the third, which gives me x cubed, but again, I've got this pesky factor of 4 hanging out here. So what do? Well, you guessed it. Take 1/4 of the expression. So 1/4 x to the fourth has a derivative of 1/4 of 4x cubed, which is exactly x cubed. So 1/4 x cubed and 1/3 x cubed and 1/4 x to the fourth are the antiderivatives, respectively, of x squared and x cubed. What could we say in general? Well, it seems like there's definitely a pattern right here. And the pattern's pretty obvious if you think about it. If I take the derivative of some function and I end up with x to the nth power, how do I do that? Well, it looks like the antiderivative has to be 1 over n plus 1 times x to the n plus 1, which certainly fits the pattern right here.